In this short video, I want to go over some of the homework and explain again how programming with recursion and pattern matching over algebraic data types works. We will look at three types of examples: integers, lists, and successor numbers. Integers are not an algebraic data type, but recursion and pattern matching works very much the same way. So this is our introduction to programming with recursion and pattern matching. List is a predefined data type. It is an algebraic data type, but we don't have to know about algebraic data types in order to understand what is going on with programming over lists. And then finally, successor numbers are our example of defining our own algebraic data type. Our introductory example to programming with recursion and pattern matching was the Fibonacci numbers. So let's review this quickly. The idea of programming with recursion and pattern matching is that we just write down the mathematical equation, and then this mathematical equation is already a program if we use Haskell syntax for our mathematical equation. So what are the mathematical equations for the Fibonacci numbers? Fib is my name for the function, and then the function takes one argument because it is supposed to compute the nth value of the Fibonacci sequence. So we start with 0. And so what is fib of 0? Fib of 0 must be the first value of the sequence of Fibonacci numbers. And maybe you can argue whether it should be 0 or 1, but let's say we start with 0. So fib of 0 is 0, and then we also say fib of 1 equals 1. And finally, the recursion works as follows. So fib of n, so to compute the next value in the sequence of Fibonacci numbers, we add the two previous values. And we just write this down as an equation. So fib of n is fib of n minus 2 plus fib of n minus 1. And that is a Haskell program. So let us review the main ingredients here. We have to find a name for the function. Then we have to think about the equations defining the functions. And typically we start with thinking about what happens for small data. What's the smallest number? We're doing here recursion about natural numbers, really. So the smallest number is 0, and that gives us our first equation. And then, because in the particular case of Fibonacci numbers, we need to add the two previous numbers, we also need two numbers to start with. So we need to add a case for fib of 1. And then finally, we add the recursive case. So one thing that is important to notice about the recursive case is that we always, in a recursion, solve a big problem, so this is computing the nth value, by reducing to solving the two smaller problems in this case. So we reduce the solution of a big problem by solving the corresponding smaller problems. So it is important here that the numbers in the recursion get smaller. To compute fib of n, we compute fib of n, but for a smaller n, namely n minus 2 and n minus 1. Okay, so let's go through some more examples. My next example is the triangle numbers. So why are they called triangle numbers? Let me just draw a little picture. So the triangle numbers is a sequence of numbers again. And as you can see, the name comes from the picture, and then we keep on going like this. And so the triangle numbers are the numbers which we get from computing the number of dots in this picture. So the first triangle number, actually I want to start with 0, so the first triangle number is 0. And then the next triangle number is 1. And then the next triangle number is 1 plus 2. So on here, right? So on this level we have 3 numbers. And then on the next level we have 6 numbers. And so on we go. So how can we write this as a recursive program? Maybe you want to stop the video and write it down yourself first. So here's an opportunity to stop the video. Okay, so I call my function triangle number. Maybe it's a bit a long word, but when I'm not writing by hand, I'm a bit faster typing, so I don't mind. And I want to keep my notation consistent with the programs I put on GitHub. Okay, so the first, or the 0th triangle number. Okay, so this looks strange. Let me try this again. So can I write a 0? Okay. So if you look at the picture, then the 0th triangle number is 0. So I just write this down. And what's the recursion here? So now you need to do a little bit of mathematical thinking. And so what is the recursive case? So I want to compute the nth triangle number. And I have to write down an equation for this. So now we need to really think about like how to go from here to here, and then from here to here. And hopefully it's the same formula each time, right? So the recursion only really works if I use the same formula at each step. And that's the formula I'm writing down here. So the formula is simply that n is 4 here, right? So let me also write down n. So n is 0 here, and 1 here, and 2 here, and 3 here, and 4 here. Right, so for example, to go from 6 to 10, I just compute 6 plus 4 equals 10. So the 4th triangle number is 4 plus the previous triangle number. Right, so the 4th triangle number is 10, and I obtain it by adding 4 plus the previous triangle number. Now that can be expressed as a mathematical equation, and I'm just going to write down this mathematical equation. So the triangle number n, the nth triangle number is n plus triangle number of n minus 1. Okay, so let's go through some more examples. The best way to learn this is really to go through lots of examples. So the next example is one that you have seen before. And it's actually the same as the triangle numbers, just replacing plus by times. So this function is known as factorial. So what is the factorial of? How do I compute the factorial? So I want to start with 0 again. And because I have multiplication now, what is factorial of 0? It's not 0. Because 0 times anything is 0. That would be a very boring sequence, only consisting of zeros. So because the neutral element of multiplication is 1, really what I want here is that factorial of 0 is 1. And then how do I do the recursion? So factorial of n is n times factorial of n minus 1. Okay, so we've seen the recursion, and I didn't talk yet about pattern matching. So where do we see the pattern matching here? So if you program factorial in another programming language, probably you've used an if-then-else. Like if the input is 0, then return 1, else to the recursive case or the iterative case. So why don't we need if-then-else here? And the reason why we don't need if-then-else is that we use pattern matching. So instead of asking explicitly if n equals 0, then else, what we do here is slightly different, and it's much nicer to write down and to read. Yeah, so we make the case distinction between n equals 0 and n not being 0 here at this point, right? So here we're treating the case where n equals 0. And the way the pattern matching works in Haskell, once we come to the second line of the program, we actually know that n is not 0. And the reason here is that this n, which I put in a magenta circle, why do we know that this n is not 0? Because Haskell is looking at all the possible different cases. So let's call this case 1, and let's call this case 2. Right? So Haskell goes through all the cases, top to bottom, and uses the first case that matches, the first pattern that matches. So if n equals 0, then the first case, the first pattern matches, and we don't try the second case, the second pattern. If the number in question is not 0, then the pattern matching here would fail, because then if the input is not 0, then this case, this pattern matching here fails. And we go instead and try case number 2. So whenever we come to case number 2, we're sure that this n here is not 0. Okay, let me scroll up just a little bit. So I gave you some examples for recursive computing with pattern matching over natural numbers or integers. And next example is recursion over lists. So let's look at some examples again. So the first example was computing the length of a list. So again, how do we build lists? Before we built numbers, the smallest number was 0, and then we had could go to bigger numbers, doing a +1 essentially, like in mathematical induction, if you've learned this in discrete mathematics. So now, what's the corresponding idea for lists? There's the smallest list, which is the empty list, and then there's an operation which we can use to build larger lists from smaller lists. So this is the empty list. And then we have a way of building a larger list from a smaller list using the colon, which allows us to construct a list from an element and a list. So all lists are built according to these two cases. Case 1, empty list, or case 2, we construct a list with an element from a list we have already constructed by some other means. Okay, so now, how can we use this idea of recursion to implement a function that computes the length of a list? I call this function len, but I might pronounce this as length. So what's the length of the empty list? Remember that we have to write our programs by writing down the equations which define these functions. So the length function is defined by two equations according to the two cases which tell us what lists are. So we need to say, what is the length of an empty list? The length of an empty list is 0. Okay, so what is the length of a list which is non-empty? Second case. So a non-empty list can be written as a list which is built by putting an element onto a list. So the element is called x here, and the list is called x's. So here we see pattern matching again. Logically, what we want to say, non-empty list, but we not only say non-empty list, we give names to the parts. The element is called x, and the tail of the list is called x's. So we use pattern matching to give names to parts of data types, to parts of data. So here we are naming the first element of the list, the head of the list, and the name is x, and we name the tail of the list, and that's called x's. And we know that the list is non-empty because case 2 is only encountered in case 1 doesn't match. And so if case 1 doesn't match, we know the list is non-empty. And so we can now just write down the formula of how to compute the length of a non-empty list. And so how do we do this? Operationally, what we do first is we compute the length of the tail of the list. We compute first the length of x's, and then we do 1 plus. That's the program that computes the length of a list. Okay, let's do another example. Imagine we have a list with some elements A, B, C, D. So actually in Haskell, if you write it like this, A, B, C, D are variables. So if you want them really to be like letters, you need to put some quotes around. And we want to, in this question, we want to select the elements at the odd indices. And I'm now violating a convention in computing, which is to count, always start counting at 0. So for me, the first element of the list is the A. And then the B is at an even position. And then the next element at an odd position, at the third position is the C. So I want to compute a function that takes as input, for example, a list ABCD and outputs AC, all the elements at odd positions. Okay, so how do we do this? We need a name for the function. I called it select odds in the file I uploaded on GitHub, but let me just call it select here. It simplifies my handwriting. Okay, so if I select the odd elements, the elements at odd positions from an empty list, what do I get? What's the equation here? So it can only be the empty list, right? Because if there are no elements to select, then all I can do is I can return an empty list. So what are the other cases I need to consider? What if, so now I need to think, right? Because in the previous examples, I needed 2 cases typically, but now I need 3 cases overall, right? So I need to distinguish the situation where the list has only 1 element and where the list has 2 elements. So this is a list with 2 elements called x1 and x2, and then the tail of the list is called x's. Yeah, so as you can see, it's probably helpful to write down first the cases maybe. So list all the cases, the left-hand sides of the equations, and then fill in the right-hand sides. That can be a helpful way to think about it sometimes. So now, second equation, the list has only one element, has exactly one element, because do I want to select this element or not? So think about an example, and I think you would agree with me that you want to select this element. So the equation should be simply this. And then for the third equation, we have to think about how to do the recursion. So we want to solve the problem again by recursively applying the function select to the smaller list, which is access here. And then how do we build the result from this? So if we look at our argument here, so we have an element x1 followed by an element x2 and then followed by a list of x's. We want to select the elements at odd positions. So we want to select the element at the first position. And so I just do this by putting this element in front of the list I already computed using the recursive application of select to access. Okay, so we've done more examples. You can also go back to the video recordings of the lectures. Let me now come to the third item, successor numbers. So far we talked about integers and talked about lists. So list is already an example of an algebraic data type, but it's a predefined algebraic data type. So really, we don't need to know so much about algebraic data types to understand how recursion over lists works. So let's build our own algebraic data type as an example. And the easiest example of an algebraic data type is one that is built just from two cases. And I write it down here again. So I call it NN for natural numbers. And I say a natural number is either a capital O or a capital S followed by a natural number. So you see that this algebraic data type is defined recursively. It's defined in terms of itself. And like it was the case with numbers and lists, there's a base case, there's a smallest natural number, which is the O. And then I can build bigger natural numbers by putting s's in front. So let's just quickly recall some examples. So the smallest natural number is just an O. And then the next biggest natural number is SO. So be careful, there needs to be a white space here. So if you write it by hand, you don't need to put the white space, but Haskell needs the white space to recognize that S and O are different tokens, different symbols. And then the next number is we can put another S in front, and here we're not allowed to forget the parentheses. So this is maybe slightly unfortunate, but it's only unfortunate if you write by hand. And this is really meant for symbolic computations by machines, this data type. So we never need to write large numbers by hand. So it's not too bad. So the parentheses, if you're wondering, reflect that the way numbers are built, right? So it's kind of very logical. The smallest number is a 0, or an O, I should say. And then we make a bigger number by putting an S in front. And then we put another S in front. And so we put the S in front of what, right? So the parentheses indicate what is the symbol you're putting the s in front of, right? And then we have another s which we put in front of, and we need to go all the way down to the last parenthesis. Okay, so our first example of a recursive program over this algebraic data type was addition. So actually, if you wondered why I call it O and not 0, at the moment, it's just a symbol. It doesn't mean anything. That's why I called it O, to emphasize that at the moment, it doesn't mean 0. It will mean 0, and that's why I chose a symbol that looks very much like a 0. But at the moment, it's not a 0. It's just a symbol. You could give it whatever name you wanted. Okay, so if we want to say that the O is a 0, we need to do something, we need to define some operations for it. So if we define an operation of addition, and the O behaves like the 0 in addition, then we can say, oh, the O is a 0. The meaning of the O is 0, right? But it only acquires this meaning once we define operations for this data. Okay, now this is an example where it's probably useful to first write down the equations in ordinary mathematical notation and then translate them to Haskell. So whenever it gets a little bit more complicated, your recursion, that's always what you should do. And so let's just think about what are the mathematical equations which define addition, right? So then let's write this down. 0 plus n equals n, right? So this defines what addition, what plus means, if the first argument is a 0. And then what if the first argument is not 0? So let's look at the case where the first argument of addition is not 0, but a number greater than 0. I write it as 1 plus n. So now we can define this addition here which refers to a number 1 plus n by an addition which refers back to a smaller number. So remember that recursion works by breaking down the problem into smaller problems. So what I'm doing here is, instead of adding 1 plus n, I ask myself, what happens if I add n to n? N is smaller than 1 plus n. Okay, so I recursively do the addition on n, which is smaller than 1 plus n, and then I put that 1 back in front, 1 plus. So let me highlight this here. So the first plus has an argument which is 1 plus n, and the recursive plus has an argument which is n, which is smaller. Okay, so I agree that maybe you've never thought about addition like this, but this is really what addition is. These are the mathematical equations that define addition of natural numbers. So once you have these equations, you can write them in Haskell. You just need to remember what is Haskell syntax for these different ingredients. So let's do this. We want to define a function. I call it add. And this add will be these pluses here. Right, so in particular, I'm going to write down add 0n as my first equation equals n. So this is just the first equation in blue, and the add is this plus here. So I could call it plus or add n for natural numbers or whatever, right? So the name add is a name that the programmer decides on. Okay, so what's the recursive case? Maybe it's worth just scrolling up a bit and remind ourselves of the data type. So we have a 0 or an O, and we have a successor. We already wrote down the equation for O, so now we need to write down an equation for S. So now we write down an equation for a number that is not 0. I need to put parentheses so that the parser that is passing the Haskell input does not get confused about where the first argument of add starts and ends. Okay, and now I do the same recursion which I written down in the blue equation above. So I add n and m. I put my parentheses and then the s in front. Okay, so let's go through one more example. Multiplication. So again, it's worth writing down the mathematical definition of multiplication first. So I need a case for 0 or for O. So what happens if I multiply a number n with 0? So 0 times n is 0. And then what is the recursive case? So suppose I have a number which is not 0. So n is a natural number, and 1 plus n then is not 0 because it's at least 1 bigger than the smallest natural number, which is 0. And so this is the familiar distributive law, right? So I just distribute the m over the 1 and the n, and I get m plus n times n. And you see, again, you have your recursion, right? So you have a multiplication, which is applied to a big number, 1 plus n, and you compute it by doing a multiplication which is with a smaller number, namely n, which is smaller than 1 plus n. Okay, so once you have this, you can easily write this in Haskell. So we need a name for our function. The name is for you to choose, but I call it mult. And we have a base case, which is the O. And we said 0 times n is 0, so O times n must be O. And then we have the inductive case. So we have a number which is not 0. I write it as Sn. And okay, so now I'm looking at the second equation in blue just above, and I basically just copy this, remembering that the plus in blue really is my add from above. So I write add, and then I write m. And now the second argument is the recursion. So I do mult and m. So I hope this helped. This is my first screen recording, so I welcome any feedback you might have, and keep on asking questions.